Yeah, so today I'll be talking about the interactions between phonons and magnetizations. Okay? So you can regard this man as phonons, and it moves in circle. So that's what we call chiral phonons with a non-zero angular momentum. Okay? And when this phonons will interact with electrons, which you can regard him, the electrons as this woman, and this woman will also move in circle, and if it carry a negative charge, it will contribute to non-zero magnetization. Okay, so this is how chiral phonons can induce a magnetization. Okay, so in the first part, I will talk about the how this phonon will generate orbital magnetization, and next I'll study the feedback effect or the reciprocal process, where the magnetization can also influence the phonon dynamics and generate chiral phonons. And from these two processes, you can see they form a feedback loop, which is a prime example of nonlinearity. Okay? So I'll show one example or one physical consequence of such nonlinearity by using a laser to drive this system. So the magnetization have two contributions. One is from spin, and the other is from orbital. For example, in a system where people can use a laser to drive a chiral phonons, and this chiral phonon can generate a non-zero spin magnetization in this parallel antiferromagnetic system. And there is also an orbital contribution, where you can see when these phonons, or if these ions carry a non-zero charge, and when they move in circle, they can contribute to a non-zero orbital magnetization. And since, for example, this phonon can carry a linear polarized phonon can carry an electric dipole proportional to the Bohm effective charge times the atomic displacement. And when they move in circle, they will contribute to a magnetization, which is proportional to this displacement cross product with the time derivative of this polarization. So this is typically in the order of nuclear magneton, which is 3 orders of magnitude smaller than the electron's Bohr magneton. But people can measure this phonon-induced orbital magnetization, for example, through this Phonon-Zeeman effect. In this cadmium arsenide, people measure this phonon magnetic moment by measuring the phonon frequency as a function of magnetic field. So you can see when the magnetic field is small, the two phonon modes, which are originally degenerate, will show a linear splitting. And this splitting corresponds to a non-zero phonon magnetic moment, which is in the order of Bohr magneton, 3 orders of magnitude larger than what we expect. And there's another measurement in lead telluride, which also show a much large phonon magnetic moment than expectation. Since these 4 elements are all non-magnetic materials, and there's no magnetic order in the system, so this contribution must come from this electron's orbital motion. So the question is, how can we describe this phonon-induced orbital magnetization? Well, from the classical expectation, it's in the nuclear magneton. So we will need a quantum theory to describe such a large magnitude. Okay, so this is the first part of this talk. So a quantum picture requires to solve the Schrödinger equation, the equation of everything. So basically, when you have a chiral phonon, which will introduce a time-dependent Hamiltonian for these electrons, and when you solve the Schrödinger equation of these electrons, you can get the ground state and the diabatic approximation. And when you get the wave functions, you can estimate or you can calculate what is the magnetization by using, if you know the operator. But the difficulty regarding the calculation of orbital magnetization is the absence of a well-defined operator in the periodic boundary condition. But the current operator is well-defined. Okay, so we can calculate the current, and using this relationship between current and the polarization and the magnetization to define what it is magnetization. Okay, this method is very successful in the last century, which when people developed the modern theory of the polarization. Okay, so we will calculate the current, and and you can define the polarization using this way, and the polarization is proportional to a geometric Bayer connection, this AK, which is related to the Bayer connection of the wave function in the momentum space, which is the K space. Okay, so when you apply this polarization to a Phonon-induced polarization, and you can get this modern definition of the bone effective charge, which is related to a Bayer curvature in the space spanned by this momentum and atomic displacement. Okay, so this Bayer curvature is different from the conventional Bayer curvature in pure momentum space. It involves the momentum and atomic displacement. Okay, so this is related to the geometric or the topological properties of these materials, so which is close to topology and correlation, which is the topic of this workshop. Okay, so we can also expect that magnetization is also have close relationship to the geometric or the topological quantities. Okay. So I'm not going to show the detailed derivation, but here is our central result, where we show that the magnetization is proportional to the Phonon angular momentum, represented as U cross U dot, and the coefficient here, the coefficient is an integral of a second term form, and those omega represents the Bayer curvatures. Okay, so the second term form, you can understand it as an analogy of the first term form, but in the higher dimensional space. Okay, so conventionally we study the first term form of the Bayer curvature in momentum space, which is closely related to a number of Hall effect, topology insulators, and quantum spin Hall effect, for example. But the second term form is a similar quantity, but in the higher dimension. And this first term form will be quantized in the closed surface in the three-dimensional parameter space, and the second term form is quantized in the five-dimensional parameter space. Even though it looks complicated, but its physical meaning is quite simple. So these two red terms represents a rotating electric dipole. Okay, so since the electric dipole is related to this bone effective charge times atomic displacement, and if you calculate this dipole cross product with its time derivative, you can use this to characterize the orbital magnetization generated by this rotating dipole. Okay. And this blue term, however, has no classical analogy. It represents a contribution from a boundary current. So that means when you have a phonon rotating inside the sample, there can be a current flowing around the whole boundary of the sample. Okay, so this boundary current can generate a non-zero magnetization, which has no classical analogy. So let me show you one example. So here we consider a gapped graphene system, and we consider a key-value carrier phonon. For this carrier phonon, this A sublattice do not move. For this B sublattice, however, they move, and there is a phase difference between neighboring B sublattices. And this is the Hamiltonian described them. And we consider the system as an electronic band gap. By calculating the system, we find that the bone effective charge is zero. However, there can be a non-zero contribution of this magnetization driven by this carrier phonon. And this magnetization is inversely proportional to the square of this band gap. So that means when the band gap goes to zero, you have a divergent large phonon magnetic moment contributed from the topological boundary current, which is a non-classical orbital magnetization. Okay, and there are also other contributions which has been studied in different papers. And this orbital magnetization has one important feature, is that since it's contributed from the topological electrons, if you use external means to manipulate the electronic structure, you can get a tunable phonon magnetic moment. For example, if you tune the electronic topology from Z2 to 1 and Z2 to 0, okay, so the same phonon can have opposite magnetic moments. And for example, in a bilayer graphene, if you use electric field to tune the band gap, where the band gap is proportional to the electric field, and you can find that the magnetization of this shear phonon will increase, will decrease the electric field. So it means there can be a very large phonon moments. Okay. And I also want to compare this phonon-induced magnetization to the inverse Faraday effect, which is from the light-induced magnetization. Okay. So the light couples with electrons through this minimum coupling. Because of this special form of this coupling, the topological contribution of the second tree form mass vanishes, which means these topological contributions can only be appear in some driven system that are different from the light-driven system. Okay. This is because of the particular form of this light-electron coupling. But in the coupling between electron and phonon, the coupling form can be much richer, and you can have different kinds of Hamiltonians described by different symmetries of these phonons. Okay. So you can have much richer physical phenomena. We can expect a novel phenomena from the coupling between between electrons and phonons. Okay, so that's the first part. We studied the carrier-phonons-induced magnetization, and its manifestation is a splitting of phonon energy under a magnetic field. Okay, so similar to the question Dan has asked. So if you have a quantum Hall effect under a magnetic field, is it possible to have quantum Hall effect without a magnetic field? Okay, so this is a question we asked. So we try to find anomalous phonon splitting without a magnetic field. Okay, so this will be our second part. Here in the second part, I will study this magnetization-induced phonon splitting. Well, we call it chiral optical phonons. Okay. So typically, we can consider the phonon dynamics by using this very simple model, which is massive particles connected by springs. Okay. And the springs represents the scalar potential where this massive ions live. Okay, so this scalar potential is time reversal even. So this time reversal symmetry will lead to several constraints on the properties of phonons. For example, the angular momentum of this phonon must be related, satisfy this relationship, where the angular momentum of phonon at minus k equals to the negative of this angular momentum at k, which means in the brilliant zone center where momentum k equals 0, the phonon angular momentum must be 0. Okay. And the second is that the phonon dispersion must satisfy this reciprocal property, or the phonon dispersion at minus k and k that have to be degenerate. And this leads to opposite phonon velocity. For example, the sound is also kind of a acoustic wave, right? So the sound speed from me to your ear is the same as the sound speed from your mouth to my ear. So that's the property of reciprocal. But when this is guaranteed by the time reversal symmetry. Okay. But if we want to have non-zero phonon angular momentum or splitting, we have to break this symmetry. Okay. So the breaking of the symmetry have two different ways. For example, you can apply a magnetic field which interacts with these ions through this Lorentz force. Okay, this is one way, but this is typically very small because the interaction between ions and magnetic field is too weak because of this large mass of these ions. Okay. You can also this magnetic field can also influence the electrons, and the electron interact with phonons through Coulomb interaction, which can be much stronger. Okay. So that's how we can break the time reversal symmetry of these phonons through electrons. And this electron can break the time reversal symmetry of phonons through a vector potential, which is time reversal odd. Okay. So this vector potential comes from a topological quantity, or a geometrical quantity from the electronic wave function. Okay. So previously we consider only the electronic energy, and we neglect the effect of the electronic wave function. But in the past few decades, we learned that when the electronic wave function forms a diabatic time revolution, it can accumulate a geometric phase. Okay, for example, when these ions move in circle, this electronic wave function will also evolve diabatically following these phonons. Okay, then it can accumulate in geometric phase. And this geometric phase can be characterized by the vector potential A. And this vector potential is the derivative of the electronic wave function with respect to atomic displacement. Okay? So this vector potential enters the Phonon Hamiltonian through similar as a magnetic field. So this term actually has been identified by Born and Huang in 1954 in their classical book about the lattice dynamics. However, they think that for stationary states, the wave function can be written as real. So they argue that this term vanishes. However, if you have spin-orbital coupling, the wave function cannot be written as real if you break the time reversal symmetry. So that's why we can have a non-zero vector potential, and this vector potential can generate an effective magnetic field on this lattice dynamics. For example, so it can introduce one additional term, which is similar to the Lorentz force through the curvature of this vector potential, and different from the local magnetic field, where when you have a real magnetic field, this Lorentz force will be proportional to the velocity of the ion itself. However, if you have a molecular barrier curvature, it's non-local, which means if you have a lattice move in its neighborhood of this ion, this moving ion can exert a force on this ion. For example, if we both are ions, my motion here will influence you. So you can feel a non-local force because of this molecular barrier curvature. This is the difference from a local magnetic field. And we can apply this theory to a Howden model where you only need to know that in this system, electronic system breaks the time reversal symmetry. So it can generate non-zero Lorentz force on the lattice dynamics. Okay? So I'll skip the detail and I'll show the equation of motion. Okay? So this is the acceleration of the A sublattice. And this is the spring constant or spring forces. And the first term is a local effective magnetic field from proportional to this velocity of A site. And this is a Lorentz force which is proportional to the velocity of the B sublattice, which is a non-local force. And you can see that these two forces are opposite. Okay? This effective magnetic field from local B field and non-local B field have opposite signs. So that means if they move together, okay, so this UA, the velocity of A sublattice and B sublattice are the same. So two Lorentz force cancel out. So there's no Lorentz force for acoustic phonons. But if they move together toward each other, okay, they have opposite velocities. This effective Lorentz force will not be able to cancel out. Okay, so they can generate a non-zero net Lorentz force and split this degeneracy of two optical phonon modes. For example, in this Howden model, if you consider this geometric phase effect, these two phonon modes are no longer degenerate and they have opposite angular momentum. Okay, so we call them carrier optical phonons. And this splitting can generate non-zero phonon angular momentum. The red branch has a positive angular momentum near h bar, and negative branch have also a negative angular momentum near minus h bar. And they can modify the Einstein-Haas effect. And the splitting can also induce barrier curvatures in phonon space and will contribute to Phonon-Hall effect. And previous example is we study a ferromagnetic system. Okay? It breaks only the time reversal symmetry. And if you consider anti-ferromagnetic system where both inversion and time reversal symmetry are broken, you can have non-reciprocal phonons. For example, this figure plots the velocity difference of this transverse acoustic phonon and the longitudinal acoustic phonons. So as a function of momentum, you can see away from this brilliant center, the velocity of phonons at k and minus k starts to be different. This is the non-reciprocal phonons. Okay, so still have 5 minutes. In the second part, we studied the influence of magnetization on this phonon dynamics. Okay, so it can influence optical phonons and non-reciprocal acoustic phonons. Okay, so these two processes form a feedback loop, and in the last part, I need to summarize it before I move to the last part. Okay, so I want to emphasize the effects of geometric phase in the phonon properties in different aspects. For example, this Born effective charge will be related to this geometric phase in the parameter space spanned by this momentum and atomic displacement. And the Bayer curvature in the momentum space will be proportional, will be related to this true number. And the geometric phase in the parameter space spanned by two atomic displacement is related to this molecular Bayer curvature. So you can see from the dipole of phonons and to the dynamics of phonons, and also the magnetization of these phonons are all closely related to those geometric quantities or these topological quantities. Okay. Yeah, so now let's move to the last part, the nonlinearity. Okay, so when we have phonons, it can influence magnetization, and the magnetization can have a feedback on this phonon dynamics. And this nonlinearity is the foundation for many intriguing phenomena like chaos or spontaneous symmetry breaking or bifurcation phenomena. So in the following, I will show you how we can generate bifurcation and spontaneous symmetry breaking in this nonlinear feedback loop, okay, by using a periodic drive. Okay, so previously in the last two parts, we focused on the orbital magnetizations. Here we turn to this spin magnetization. And recently in experiments, they have already demonstrated that if you have phonon, which with a non-zero phonon angular momentum represented by this Q cross Q dots, it can generate a non-zero spin magnetization. Okay, and here Q represents this phonon coordinates, and this S is spin, and the G represents the spin phonon coupling. And the reciprocal process means that if you have a non-zero spin magnetization, you can generate a non-zero effective magnetic field on this phonon dynamics. Okay, so you can induce this phonons energy splitting. For example, in last century, in the same material family, people have already observed that if you apply a magnetic field, generate a non-zero spin, and this non-zero spin can generate an effective magnetic field for these phonons and induce phonon energy splitting. So then we can focus on this material because it has strong phonon spin coupling, and both processes has been identified. Okay. Now we apply a linearly polarized drive to the system. So this part describes this phonon dynamics. This is kinetic energy, and this is this spring constant. And this part is the spin phonon coupling, and the last part is a coupling between light and phonons. We assume that this phonon carry a non-zero dipole proportional to the Born effective charge, and this dipole can couple with external electric field. Okay, so this whole system has a mirror symmetry. About the X-plane. This mirror symmetry guarantees that the net magnetization along z direction must be zero. Okay? And the system cannot have angular momentum and magnetization. Well, but we can examine whether the symmetry is still there or is broken by solving this time-dependent equation of motion for these phonons and spins. And this phonon can experience different forces, from the spin forces to driving forces, and this effective magnetic field from spin. And this is this dissipation term we get by hand. And the spin follows a relaxational dynamics following the Bloch equation. Okay? By solving this equation, we actually find that initially the system actually form a linear motion, but as time evolves, the trajectory gradually becomes elliptically polarized, and finally it forms a limit circle, which is a closed orbital with non-zero angular momentum. Okay, this figure shows angular momentum as a function of time. Okay, so this result shows that under certain conditions, the system can broken the mirror symmetry and generate a non-zero angular momentum and magnetization. Okay? And because of the symmetry, there are two choices of this final angular momentum, either positive or negative, selected randomly by the fluctuations. So that's why we call it a spontaneous symmetry breaking. And this spontaneous symmetry breaking requires a large enough driving force. And when the driving force is weak, the steady state have a linear polarization with zero angular momentum. And when the driving force is large, it can have a non-zero angular momentum. And this is the phase diagram as a function of driving force and driving frequency. It needs a large enough driving force. So I'll skip these details, but there's some potential material candidates where you can find, where you propose you can find this phenomena, for example, in cerium fluoride or this cobalt compound with strong spin-phonon coupling. Okay, so this is a summary. We studied the three processes where phonon can generate magnetization, and magnetization can influence phonons. And if you drive this whole system, there can be nonlinear processes. And the interplay between phonons and magnetization can lead to many intriguing phenomena. For example, we can generate non-zero magnetization in a non-magnetic system. Okay? In ferromagnetic system, we can have carrier optical phonons, and in antiferromagnets, we can have non-reciprocal acoustic phonons. And in the paramagnet, there can be nonlinear feedback loop. Okay, and at last, I would like to thank my postdoc supervisors, Qian Yu and Di Xiao. Most of these works are done when I was a postdoc. So I hope in the future I can talk something I did myself. Okay, thank you.